Okay, this video is going to help you get started using the ModelSim VHDL simulator, and we'll do that by working through practice problem 5.10e in the textbook. Okay, so to begin with, let's take a look at what the problem is, 5.10. So what we're going to do is we're going to implement this truth table right here, 3-input truth table, in VHDL using concurrent signal assignments with logical operators. And what we're going to do is we're going to design the system for this, and then we're going to simulate it with VHDL. So the first thing we need to do when we use concurrent signal assignments with logical operators is actually we have to design the logic that we're going to implement. So this is not the greatest way to actually do VHDL because it's not allowing the tool to synthesize for you, so it's a little bit more, lower level. But anyway, let's just work through it. So why don't we form the canonical sum of products for this truth table, and we can do this very quickly. So the first thing we're going to do is create the minterms for every output that's equal to a 1. So the minterms for row 1 are going to be A naught B naught C. For row 3, they're going to be A naught B C. For row 4, they're going to be A, B naught, C naught, and for row 6, they're going to be A, B, C naught. Alright, so then that will form our logic expression, which is simply all the minterms ORed together. And then finally, we can have our logic diagram, which is going to be this. So what we're going to do is we're going to need to implement this in VHDL, and so we're going to use the logical operator NOT to implement the inversions of our inputs. We're going to use a logical AND in VHDL to perform this first stage of product terms, and then finally we're going to OR those all together and form the actual output. Alright, so let's get started by looking at ModelSim. The first thing that happens when you run a logic simulation is you need to have a test bench. So I'm going to provide you with a test bench which is called system E_TB. The TB is test bench. System E stands for it's the truth table E in the textbook. And what you are going to do is we're going to design the system E.VHD, and that's going to be the VHDL file that will be simulated. So we call this a DUT, or device under test, but really what this is we're going to create this system E.VHD. What a test bench does is it will instantiate your VHDL file, or your design, and then it's going to have these internal signals that it's going to wire up to your inputs, and that's going to have a signal that's connected to the output of your system, and then it's going to use some behavioral modeling to generate stimulus that will then drive in all possible input codes into your system, and then you should be able to look at the outputs. So we're going to get a logic diagram or a logic waveform out of this simulation, and we can use it to verify whether the output of our system is actually what the truth table intended. Okay, so the first thing we're going to do is we need to get the test bench, and the test bench is out on Desire to Learn. So what I'm going to do is I'm going to create a folder to stick the test in, or the test bench in, and then we'll create our design file in that same folder. Now typically you want to create a folder for every design because when you launch ModelSim you're going to start a project, and those projects are going to create files that you compile your work into, and it'll hold all the values of your simulation. So each VHDL simulation needs its own folder. So I have a folder on my desktop called 261 VHDL. And within it I created a folder called ModelSim, and let's create a new folder called, let's call it System E. Yeah, that's probably good enough. System E. So now in here I need to go get the test bench and download it into here. Now the test bench is just a VHDL file, so I'm going to go out to Desire to Learn. And for the practice problems, if you go under content, what you're going to see is that if you scroll down, you have these 4 VHDL files. And so this is Chapter 5 Test Bench System E_TB.VHD. And the way that you download these in the practice or in the content area is you just click on that little down arrow and you hit download. Okay, so it's downloading it. I'm using Chrome, so it just pops it down here on this little fella. And I drag it over. So now I have something called System E_test bench. At this point I can start a ModelSim project and actually do the simulation. So you're going to find ModelSim in all the Cobley 5th or 6th floor computers, and what you do is you go down here to the Start menu, and what you're going to look for is All Programs, and it is actually going to be under a folder called Altera. And it doesn't really matter which version of Altera, use the latest version, but you're looking for the web edition, and you can actually go out and download this from Altera's website. So underneath one of the web editions, you're going to go under ModelSim Altera Starter Edition, and if you click that, you'll see ModelSim Altera 10.1D. So you go ahead and click that, and this is going to run the ModelSim program for you. So this will come up, and this program is it's a hardware description language functional simulator, and this is what we'll use to actually verify that our design works. Okay, so we wait for it. Okay, so here it is, and it comes up and it looks like this. Okay, so now what I'm going to do is the first thing is I'm going to start a project. So I come into here and I say File, New, Project. And what I'm going to do is I'm going to give it a project name, and I'm going to give it the project location. This is very important that you browse to the location of where your test bench is, because you don't want these files being compiled all over your computer or all over your hard drive. You want to keep them contained. So what I'm going to do is I'm going to come back to my own desktop, and I'm going to go into my desktop folder called 261 VHDL, ModelSim, and then here's our System E. So I give it that path, and I need a project name. It doesn't really matter what you call it. You can just call it System E Project. Now, one of the more important things here is that there's a library, default library name called Work. Do not change that ever. What's going to happen is as you compile and run simulations, all your information is going to go into this work directory, which will be created by ModelSim, and it's always looking for the keyword work, so don't ever change that library name. And I go ahead and say OK. So now what ModelSim does is it creates this folder, or creates this project, and it's going to say, all right, if you weren't going to run a simulation, let's get some VHDL files in here. So I'm going to do add existing file, and the first thing I'm going to do is add my test bench so that it's in there. So you say open or browse, and it goes directly to the folder of your project, and I find my System E _ test bench. So I go ahead and say OK, and it's just going to say reference from current location, leave everything the way it is, go ahead and say OK. And now I can close this, and now I have a file in here. Now the way this works is that you have this file and it's got the status. Right now this doesn't know if this is compiled yet. So I can double click on that and it'll bring it open in a text editor. And what's nice about the ModelSim text editor is that it actually has all the keywords colored and everything. So you can come in here and you can look at a test bench. You don't have to know what this does right now. All you have to know is that it's looking for something called System E, and that's what we're going to create. So now I'm going to go ahead and compile this and make sure everything's good. So I right click on it, say compile, and compile selected. You're going to see your status down here under the transcript window and it says compile was successful. So this is good, our test bench works, which we expected. Now what I'm going to do is I'm going to add to project a new file. So I right click over here in the project tab. Now notice down here I have a project tab and a library tab. I'm in my project tab, that shows me my file. I right click and say add to project, new file. It's going to ask me the file name. I'm going to browse and make sure that it's in the right spot. So it's going to put it in, desktop 261 VHDL ModelSim System E. So it's in the right spot, and I'm going to call it System E. So I take that System E.VHD. Now this is my design file. All right, so it's not the test bench. The test bench had _TB standing for test bench. This is actually my regular design file, and it's going to add it as type VHDL. So let's take a look at this. Does it? Okay, there it is. I go ahead and double click on it, and it's blank. So at this point, I'm ready to write VHDL in order to implement this truth table. So let's come along. I'm going to pull this over and let me get up my the design that I'm trying to do. And there's the functionality. There's what I'm trying to design. So I'm trying to design. Let me put .VHD on here so it makes more sense of what we're doing. Alright, so I'm designing system E. So the first thing I'm going to do is create the entity for this. So I'm going to type entity, and I need to name it system E, and then I say is. And the first thing I'm going to do is a port definition. So I say port, and I'm going to define A, B, and C. So I'm going to go A, comma B, comma C, colon, and now I need to give it the type, which I'm going to say is bit, and the mode, which is in, and then semicolon. Okay, so at this point I am going to continue adding. Okay, I have that backwards. It's actually, I give it the mode in, and then I give it type bit. Okay, then I'm going to, oh look, you notice that the keywords will turn colors. It kind of lets you know what's going on, that you're doing everything right. So then I say F, and that's my output. So I'm going to give it a mode of out and a type of bit, and then I end the port definition. And what I'd like to do is I like to line up like, you know, the modes and the colons and everything, just to make it look a little bit better. Remember on the last colon or semicolon, when you do your port definitions, it goes outside of the parentheses. And at this point I'm ready to say end entity colon, and I'm done. And then I line it up manually. Alright, now I'm ready to do my architecture, which will describe the behavior of this. So I'm going to say architecture, and I got to give it a name. What I do is I say system E underscore arc. That tells me this is an architecture. You can name it anything you want, but I always try to relate it, make it something meaningful. An architecture needs to be linked to an entity, so I say of, and I give it the entity name. So I say system E, and I say is. At this point, I'm ready to come down and I can do any signal declarations, component declarations, type declarations, whatever I want to do, and then I'll do a begin statement. What I'm going to need is I'm going to need to declare some internal signals in order to implement this circuit. First thing we're going to need is we're going to need inversions of each of our input variables. So why don't we go ahead and create signal names that are going to be AN for A naught, BN for B naught, and CN for C naught. And then we can, the first thing we'll do is we'll create those signals by using the not operator. So I'm going to come in here and I'm going to declare a signal. So I'm going to say signal, and I do, let's see, if I ever forget how to do the syntax, I always go look at the test bench. So it's like, okay, so I do signal name, colon, and then type. So I go signal name, AN, BN, CN, colon, type, I'm going to give it bit. Alright, so I just declared those signals. The other thing we're going to need is we're going to need internal signals for these nodes right here, which are the outputs of the product terms. Now what I'm going to do is let's call them, since this is a canonical, why don't we go ahead and call these like minterm 1, minterm 3, minterm 4, and minterm 6. And that way what we can do is it kind of tracks like the canonical approach we're taking. So this will be minterm 1, minterm, this will be minterm 3, this will be minterm 4, and this will be minterm 6. Okay? And we'll create the logic for those using logic operators, and then finally we'll OR them all together and create F. Okay, so now we're ready. So I'm going to put that over there. So we need those 4 signals. So I'm going to come along and I'm going to say signal M1, M3, M4, M6, colon, type, bit. Alright, line these up, and I'm good to go. At this point I think that's all I need, so I'm going to go ahead and do a begin. And after the begin statement, I will put the logical or the signal assignments. So at this point, let's begin with creating the inversions for the input variables. So I'm going to say AN, this new signal I created, is assigned the inversion of A. So AN is equal to not A. That's a signal assignment operator, and that, or a signal assignment operator, and this is a logical operator. This is called a concurrent signal assignment with logical operators. Alright, now I go ahead and do some copying and pasting here, line everybody up, and I can create the inversions for B and C, and I simply have BN gets assigned not B, Cn gets assigned not C. I have done my first stage of inverters, which is my NOTs. Okay. Now I can pump those into these AND gates. So the AND gates over here are going to drive these signals M1, M3, M6, and M4 and M6. So what I'm going to do is I'm going to do a signal assignment to M1, which will be A naught ANDed with B naught ANDed with C. And I simply do AN, which is my signal that I am driving here, and I use the keyword AND to AND that with BN, which is the signal I created here, and then I AND that with C. That has created this min term. Okay, so now I can do a similar thing here. I'm going to create M3, and that is simply A naught B C, and then I create the min term 4, and that's simply A B naught C. So I come over here and I say A B naught C naught. And then finally I do min term 6, which is just A B and then C naught. Okay, so at this point let's double check. What I'm trying to do is create these product terms. So I've got A naught B naught C, so I got A naught B naught C, I got A naught B C, so I got A naught B C, I got A B naught C naught, A B naught C naught, and then I have A B C. Okay, good. So I got those together, and now finally I'm ready to create my output F, which is the output port of this thing, and I simply assign to it M1 ORed with M3, ORed with M4, ORed with M6. I'm done with my functionality, so I end my architecture, and now it's time to compile. Alright, so I'm going to compile and fix all the syntax errors that I have in my design. Very rarely can you get through one of these without having some syntax error. And so I'll go ahead and save this, and let me comment this. This is going to be my ANDs, and down here I'll have my ORs. Okay, so I save this guy up. I come in here, right click, and I say compile selected. Holy moly, this worked. So I actually wrote the entire thing without any syntax errors. That'll rarely happen. So I'm ready. My test bench is compiled correctly, my design is compiled correctly. Now I need to simulate it to see if it actually works. So now what I do, here's how you simulate. You go into the library tab, and you're going to scroll down to the bottom. You're going to find your work directory. You expand that, and you're going to see System E and System E test bench. There's no case in these things. You are going to load the System E test bench by double click on it. So I double click, and it brings up a simulation, and you'll notice this tab now, which is a waveform, and there's nothing in it. I have to add the signals to it. So I'm going to come over to this field right here, and I right click and say add to wave signals in design. And look at all these things right here. So I have my test bench signals, which are driving the ins and the outs. I have the A, B, and C, F. I also have A, N, B, and C, N, and my M's. And so I can actually see if this is going to work. What I'm really interested in is the TB signals. These ones right here, because they're going to show me what the inputs from the test bench are and the output observed by the test bench. So those are the ones that I really care about. If I wanted to delete some signals, I just highlight them, right click, and say delete. Well, edit, delete. If I only wanted, I can bring these in also, so I can go edit, delete. I could go over here and say add to wave all signals, or selected signals, all signals in regions. I could say selected signals. That gives me now just the 4 I want. I'm ready to run a simulation. Now it turns out that this one runs, it goes through 8 input codes every 100 nanoseconds, just the way that simulation is set up, or the test bench. So I'm going to run this for 1 microsecond. This button right here is run, so I hit run. Now it's simulated. The first thing you see is you see these output waveforms. You're zoomed way at the end, so if you scroll back you can see them transitioning. First thing you do is click in here and right click and say zoom full. At this point you actually have waveforms here. So now this is good. So if you take your cursor, if you just click anywhere and drag around and pull it back to here, you can see that this code right here, it's showing you that A, B, and C, their input values, and the output F. So I have 0, 0, 0 gives me a 0. 0, 0, 1 gives me a 1. 0, 1, 0 is a 0. 0, 1, 1 is a 1. Now if I look at that, I need to kind of verify that that's actually correct. So I'm going to drag this over, and I want to get my truth table on the screen here so I can see. So I'm supposed to be getting this circuit right there, that truth table. Okay, so for, let's see, 0, 0, 0, I got a 0. For 0, 0, 1, I got a 1. For 0, 0, 0, or 0, 1, 0, I got a 0. For 0, 1, 1, I got a 1. Good. Then for 1, 0, 0, I got a 1. For 1, 0, 1, I got a 0. For 1, 1, 0, I got a 1. And then I got, for 1, 1, 1, I got a 0. Then the simulation starts over. So I indeed verified that I have the correct truth table. Now this is actually kind of hard to see because these inputs are scalars. So one of the neat things you can do is I can group A, B, and C into what's called a bus. So I can say combine signals. Let's see, combine signals, and I'm going to call it ABC in the result, and it tells you how do you want to do it. You want the top to be your most significant and descending and all that stuff. Just leave it as default, and it'll always put the top as your most significant bit. So now check this out. What I've done here is I've created something which groups them together so I can see it a little bit more intuitively. So now at this point, and I can move these signals around. So now if you look at this, this makes way more sense. 0, 0, 0 gives a 0. 0, 0, 1 gives a 1. 0, 1, 0 gives a 0. 0, 1, 1 gives a 1. 1, 0, 0 gives a 1. 1, 0, 1 gives a 0. 1, 1, 0 is a 1. And 1, 1, 1 is a 0. I have implemented this truth table correctly, and it's easy to see. To make it even easier to see, I can change the radix of this bus to an unsigned value, and it'll show me the decimal value. The reason that that's really handy is because the truth table is formally defined so that each of these minterms actually correspond to a row number. So this is row, I should be getting a 1 on row 1, I should get a 1 on row 3, I should get a 1 on row 5, and oh, did I screw this up? I did screw it up, didn't I? And I should be getting a 1 on row 7. No. What am I looking at here? Sorry about that. I'm looking at these guys right here. Let me get rid of those. Delete these so I can see. Edit. Delete. Now, here's what I got. Row 1 is a 1. Correct. Row 3 is a 1. Correct. Row 4 is a 1. Correct. Row 6 is a 1. Correct. We got it. And the simulation continues. So now I'm done with that. If I was going to turn this in, if this was my homework problem, what I would do is do a screenshot of this waveform. And the way you do a screenshot is you hold Alt down and you hit print screen on your keyboard. The Alt will do a capture of just the window you have selected. And then you can go into like Paint and just paste it, and then save it as a JPEG and shrink it down so it's about, less than 500 kilobytes. Okay, that is it. So that was a tutorial on how to actually start a project in ModelSim, download the test bench, create a file, and what we did in VHDL is we created the functionality for this truth table using concurrent signal assignments with logical operators. Now, that's it. Alrighty.